And our next topic is all about the idea of sorting. So let me draw a picture for you for a second, quite literally. And what I mean by that is, let's get down in here. Imagine for a second that you went bowling. I'm sure you've all gone bowling before at some point in your life. And when you go to the bowling, you go up to the counter because you got to rent a pair of shoes. And you get to this nice warm counter up top, and there's a dude behind the counter, or a woman, doesn't really matter. And when you get up there, you say, "Hey, can I please have a size 10 shoe?" And within about 2 seconds, that pair of shoes is sitting on the counter for you. Now, if you were to look behind that counter, what you would see is a massive grid. And I'm talking hundreds and hundreds of identical looking shoes. And each one is stuffed. Each pair of shoes is literally stuffed into a box. And somehow that employee is able to pull out your exact pair for you within seconds and have them available for you. How is that even possible with hundreds and hundreds of pairs of shoes behind the counter? How are they able to get the right one in that kind of time frame? This is a human being. We're not talking about a computer. We're not talking about a Google search here. We're talking about a human being. Well, quite clearly, the answer is simply organization. Every bowling alley organizes their shoes by 2 factors: gender and size. The reason why they do gender, of course, is because the size vary based on gender. A size 7 shoe for men is not the same as a size 7 shoe for women, so it doesn't make sense to keep the genders together. So let's assume this is one of the genders here. This grid is one of the genders. And then they'll organize it and they'll say, okay, this is size 5, 6, 7, 8, 9, and so on and so forth. And they'll keep going down all the way down the grid. And the thing is all of that entire row will be size 5. All that entire row will be size 6, 7, and 8, and 9. So all the employee has to do is literally bend over, reach in the correct row, and pull out a pair of shoes as long as it's available. They're going to, of course, go over and find the first available because maybe this box is empty and this box is empty, but this one has the shoes that they're looking for. So they grab the first ones. They plop them on the counter. This organization is the only thing that allows this to happen. If you returned your shoes and they just stuffed it into a random box afterwards and there was no organization, those 2 seconds that it takes to find your shoes would turn into 2 minutes because they'd just be going trial and error, looking in each pair, trying to find the right size. Trust me, I know this. I used to work in a bowling alley. So if people put the shoes in the wrong spot, there's nothing more frustrating as an employee to deal with that kind of thing. So the organization is what's really key here. This is why we're learning about sorting. The whole point behind computer science is dealing with large scales amounts of data. And what do I mean by that? I mean thousands, millions, even trillions of pieces of data, and us having to locate the specific one that we want. Just imagine how Google searches for all of its stuff. Now, it does a lot of fancy things behind the scenes, but it basically boils down to organizing the data so it knows exactly where to look for something at the right time and at the right place. This is our goal. So before we can search for our data, we need to be able to organize and sort our data. That is today's topic. So, there are a lot of different sorting techniques out there, and they're not all created equal. In fact, some techniques are super duper costly, whereas others are not costly at all. They're very cheap, they're very quick. But sometimes that can depend on the data itself. The type of data, the already organized state of the data. Some algorithms, for example, may be very quick if the data is almost sorted already. Some algorithms, they won't care how sorted it is already. It'll take the same amount of time every single time. It depends on the strategy that's used. So in this course, we're going to learn 3 types of sorting algorithms. 2 of them are iterative and 1 of them is recursive. So the insertion sort and the bubble sort is going to be covered in this lesson right now. And then the next lesson we're going to talk about that merge sort, and that's a recursive sort. And it's a very efficient sort. Both of these iterative sorts are actually not very efficient at all, but they are very easy to code. And that's the benefit. Sometimes the speed of coding is your priority and not necessarily the speed of the execution of the code. Maybe you just need to get that product out the door as fast as possible. Who knows? So there are a ton more sorts out there. 3 is by far not the magic number here. If you dig into it a little bit, you can find dozens and dozens of different types of sorts. So let's start off by watching a little video. Now you can click on this on your own, but I'm going to put the video on here so everybody can see it. So this video is all about random data. I'm going to skip certain parts of it during this presentation. You can go watch it on your own later on if you'd like, but I just want to emphasize the relationship between all these different sorting mechanisms. Oops, that's not what I meant to do. All right, let's get into this now. Now pay close attention to the different names. Up the top left we have a selection sort, then we have a shell sort, and an insertion sort, the merge sort, the quick sort, the heap sort, the bubble sort, the comb sort, and then the cocktail sort. And again, these are not all the types of sorts that exist. But you saw how fast the merge sort was, how fast the quick sort was. The insertion sort and the bubble sort, the ones that we're going to be covering in this lesson, they're still trucking along. The insertion sort's doing okay. Bubble sort, not even close. If you look at the time frame of the video, it's only about a 4-minute video, so I'm going to skip ahead here just to see how far we got to go. So we're 40 seconds in here. Let's see how far we got to go. There we go. So at about a minute, it took about a minute to do that sort. Now that's obviously not real time because it's visualizing the actual data, right? Now see, the quick sort's already done here. Ooh, that was quick. Merge sort's coming in next. And wait, watch this. And it joins. We're done. Again, here's the bubble sort taking up the rear. It's going to take its time. Their insertion sort's not doing too much better, but it is looking a little bit better. Okay, so let's move a little forward. Now, if you didn't notice what this one represented, I'm going to go back for a second. This organization right here, the first set of data was completely randomized data, which is your average data set. But this one right here that we were just watching a second ago, come on, finish up bubble sort, is when you only have a few unique, which means you have a lot of duplicate data. Now going past that point, the next one is when we have the reverse data, completely reversed. So everything's in the opposite direction. This is much prettier to watch, but watch that quick sort go. The insertion sort's not doing too bad. Bubble sort, taking its time. Just by watching these algorithms, I wonder if you can figure out how they actually operate. The bubble sort looks like it's pretty clear, but maybe you haven't caught on yet. So feel free to watch. Okay, we're going to move on now because this is going to take a while if we just sit here and watch. We're going to fast forward. Come on, bubble sort. You can do it. We've all got faith in you. It looks like it's accelerating. It's really not, though. Come on. And we got one more left where the data is almost already sorted. There's only one data element that's not there. Oh, look at that. The insertion sort won. Ooh, the insertion sort beat the quick sort, beat the merge sort. Well, that's interesting. How did it go from like second last to first? Well, it's all based on how it gets to that, or how it organizes those elements, and what it needs to do every step of the way when it finds something that's out of place. In fact, they all work like that, to be honest, but their way they organize things is what matters. And now the bubble sort's done. Bubble sort beat something for a change. It beat that selection sort. Wow. Okay. So what you saw here was a selection of 9 different sorting algorithms. And like I said, there's dozens and dozens of sorting algorithms out there, probably more than that. And some of them are useful. And now you might say, why are there so many? Why doesn't everybody just choose the fastest one? Well, the thing is, because the fastest one isn't always the fastest one, depending on the type of data that it's working with. What I mean by that is, with these types of elements that we saw random sets, we saw almost sorted set, we saw reverse set, and based on that, it's not always the best choice to go with what seems to be the fastest one. Another factor comes into how many elements you're working with. If you're working with 10 elements of data, it doesn't matter which one you choose. It's going to be fast no matter what. You're not even going to notice the speed. So what's your driving factor in choosing the algorithm to use then? Well, it's no longer the efficiency of the algorithm, it's the efficiency of you implementing the algorithm that comes up that point. And if that's the case, then you're going to be implementing either the insertion sort or the bubble sort, because those two are the fastest and the easiest to actually code. And that's why we're going to be looking at them first today. Oops. So the insertion sort. I'm going to do this through a diagram just so we can actually see how this works. But how does this actually work? So we're going to begin with the insertion sort. What you need to know is that if this thing actually takes very little data to function. So it has its original array of data, and the only other thing it needs is a single variable to store a temporary, one of the values in a temporary location. And that's so it can perform a swap. If you guys remember how we did a swap way back where we had two variables, and we stored one in a temp variable, swapped the two there, and then brought that temp variable back into the original one, or back into the other one. So that process occurs here. Now, what I want you to do is I want you to think of the data as a grouping, like an array. So if I look over, let's go over to my drawing here for a second, and let's draw some information. Let's say, first of all, we're going to be doing our insertion sort. Let's turn on our pen, that would help. Okay. So first up, we're going to do an insertion sort. Insertion sort. Great. I'm going to start off with this piece of data here. So I'm just going to make up some numbers here. So maybe we have 9, 3, 6, -2, 5. That's probably enough. We got 5 numbers there. Now, if this is an array of integers, we usually use integers when we're thinking about this because they're pretty easy to visualize in terms of greater than, less than type thing. Now, we want to organize this. We want to try and sort it in ascending order. So smallest at the left, largest at the right. And that's our goal. So the way the insertion sort works is when we're looking at this data, what we want to do is we want to visualize this data in 2 chunks, a sorted chunk and an unsorted chunk. And for an insertion sort, we are going to assume that that first element is already sorted. So we're going to, let me just make this a bit bigger here. So we're going to assume that first element is already sorted. So everything on this side is sorted. Everything on this side is unsorted. Well, how do I know that that 9 is sorted? Well, because there's only one element. One element by definition is sorted. So how does the actual algorithm work now? What do we actually do? Well, now what we're going to do is we're going to grab the first element in the unsorted section and we're going to insert it into the correct place in terms of size in the sorted section. So how does that actually work? Well, we take that first unsorted element and we compare it against the sorted elements in order from right to left. And we say, okay, is the sorted element bigger than the element I'm trying to insert? If yes, then shift it over to the right. If we finally get to an element that is smaller than the element we're trying to insert, then that place, that location just to that smaller element is where we're going to insert the data. So let's demonstrate that. So this first one, when we do this, the 9 is going to get shifted to the right, and then there's no more places to go, so that means the 3 gets inserted right at that element. So after the first step, we have 3, and then 9, and then this is our sorted section now. And over here on our unsorted section, we have 6, -2, and 5. And now the process continues. So now we start at the 6, the first unsorted element, and we compare it against the first sorted element. So is 9 greater than 6? Yes, it is. So the 9 gets shifted, and then we check the 6 against the 3. Is the 3 greater than the 6? No, it's not. So that means the 6 gets inserted just to the right of the 3. So now after step 2, we have 3, 6, 9, that's our sorted section, and then we have -2 and 5 in our unsorted section. And the process continues. So, is 9 greater than -2? Yes, it is, so it gets shifted. Is 6 greater than -2? Yes, it is, so it gets shifted. Is 3 greater than -2? Yes, it is, so it gets shifted. And we don't have any place to go now, so the 2 gets popped into that last spot. So after 3 steps, we're at -2, 3, 6, 9. That's our sorted section, and our unsorted section is just the 5. And it goes through the same process. We are trying to insert that 5 into the correct location. So, is 9 greater than the 5? Yep, so it gets shifted. Is 6 greater than 5? Yep, it gets shifted. Is 3 greater than 5? No. So the 5 gets inserted just to the right of the 3. And all said and done, after 4 steps, we're at -2, 3, 6, 5. Oops. Control Z. 5, 6, 9. And now we have our sorted array. It only took 4 steps. That's not too bad. So when we're looking at this, the algorithm is fairly straightforward. You're just trying to insert it, and for every number that's bigger than it in the sorted section, you're just going to shift it to the right. Eventually, you're going to find either the end of the list, or you're going to find an element that's smaller than the one you're trying to insert, in which case, that's where you're going to be inserting, just to the right of that element. Okay, so what's the time complexity of this algorithm? What are we actually looking at in terms of what it's going to take to actually run this algorithm? Well, first of all, in terms of memory, not much. The only thing we're going to need is one little bucket for temp data. And that's for when we do the swap. So when we shift those values over, we need to store that variable that we're going to be inserting in that temp variable. So on the first step, we're storing the 3 in this temp variable. And that way, when we shift things over, we don't have to worry about overwriting our 3. That 9 just takes its place. But that's okay, because we still have the 3 stored, and we're not going to lose it. Just like over here in the second step, we're going to be storing that 6 in the temp variable, right? And that's the only data that we need in terms of extra data. So we say our data is big O of constant. It's a constant amount of data needed. Doesn't matter how big our array is, we still only need one element, one integer to do this. In terms of time, well, this is a little bit more interesting. We have to look at every single element that's unsorted. Well, that's n minus 1 elements, right? And we have to compare that against all the sorted elements. And that sorted element collection basically grows to eventually it's going to be n minus 1 elements. So in that worst case scenario, we're looking at n minus 1 altogether. Now, at the big scheme of things, when we think about this, how n grows to infinity, that minus 1 becomes insignificant. So we end up with n times n, which is, of course, n squared. So the worst case scenario is big O of n squared. This is the time complexity of the insertion sort. As we saw before, what does that curve look like? Well, it's not pretty. It's going to look something like that. So as n increases, the amount of time it takes to actually implement this structure is not great. There is a lot of way better algorithms out there. But if you're dealing with very little data, this is actually a fantastic algorithm. We actually saw it beat all of the other algorithms when the data was almost sorted, when we only had one thing to implement. And the reason being is that there's going to be very little shifting if that's the case. If we only have one element out of the spot, that means our sorted collection starts here. That means everything is already sorted except for the one element. It makes the algorithm super duper efficient. At most, at worst case scenario, it's big O of n, if that's the case. So that's awesome. But of course, that's not really the normal case. It actually wouldn't be big O, it would be big omega, which means best case scenario. Okay, let me just do some erasing here. So that's our first algorithm. That is the insertion sort. Let's take it over and look at the bubble sort now. So we're going to do a bubble sort on the exact same collection of data. Now, I'm going to draw this out for us again. But I do need to introduce you to a couple concepts before we do this. Where's my pen? So bubble sort. Now the bubble sort is probably the most commonly implemented sort out there when efficiency is not your factor here. And the reason being is because it's extremely fast to implement. Only a couple lines of code, not including the swap code, right? And it's very, very quick to actually create. There's very little logic involved other than some basic comparisons, which you're going to see in a second. So it's similar to the insertion sort in the idea that we have a sorted section and an unsorted section. But how it differs is where that sorted section is and how we deal with it. So let's write our original data again. So we start with 9, then we have 3, 6, -2, and 5. So the question is, where does the sorted section start? Well, the sorted section starts at the end, right here. And currently it has 0 elements. So sorted is at the very end. And the unsorted is everything else. Oops, unsorted. There we go. And it currently has n elements. All right. So what's the key to this algorithm? How is this actually going to work? Well, basically what our goal is to get all of our elements into the sorted section. And this is going to happen one element at a time. We can't group things together or anything like that. So we're going to take all of our unsorted elements and eventually get them over to that sorted collection. How are we going to do that? Well, with some comparisons. We're going to start by comparing the first two numbers. So think of it like this. I'm going to use blue for this. So I'm going to compare element 0 and element 1. And if element 0 is bigger than element 1, then I'm going to swap their locations. So in this case, they are. So what's going to happen here is after this first comparison, we're at 3, 9, 6, -2, and 5. And now we repeat this process again. But now we're going to compare 1 against 2. And we say, is 1 greater than 2? Yes, it is, so we swap. So in this case, now we have 3, 6, 9, -2, and 5. Okay, and the process continues. And now we're comparing 2 against 3. So what you can see here is this largest number is working its way up to the end of the collection. So is 9 greater than -2? Well, of course it is, so we're going to swap again. So now we're at 3, 6, -2, 9, and 5. And now we're finally going to compare element 3 against element 4. And we compare again and say, is 9 greater than 5? Yes, it is, so we swap. 2, 5, and then 9. And now there's no other comparisons to be made, so I know that I'm at the end of that collection, and I officially have one element in the sorted section. Let me draw that a little bit better. So we officially have one element in the sorted section. Guess what happens now? The whole process repeats again. So I'm gonna move up to the right here and restart where we're at. I'm gonna rewrite the numbers. So we're at 3, 6, -2, 5, and 9, but that 9 is sorted. So now the whole process continues, but we don't go all the way to the end now. We only bubble up the numbers up to that sorted section. So if we start over again, we say, is 3 bigger than 6? We compare 0 against 1. No, it's not, so no swap occurs. So we go in and we check the next one. And we say, is 6 bigger than -2? Well, yes, it is. So we swap here. So now all of a sudden we're at 3, -2, 6, 5. And now we do the next comparison. Is element 2 bigger than element 3? Yes, it is. 6 is bigger than 5. So we swap. So we're at 3, -2, 5, 6. And the sorted, I forgot to write the sorted element there. We're now at that sorted collection, so we don't need to swap any further. So now that sorted bar just got moved over. So we're done this next step. So we do it all over again. And we come back up. And now now you can start to see why this one always took longer than everything else, because there was a lot more work involved, a lot more swaps involved, and things like that. And those swaps are pretty expensive when you think about it. So now we're at 3, -2, 5, and 6, and 9. But we have 2 of them already sorted. So the whole process begins again. Oops. Where's my blue? Here's my blue. So we're going to compare element 0 against element 1. And is element 0 bigger than element 1? Yes, it is. So the -2 it comes over here. Where's my... Yeah, that's right. So our -2 comes here, and then we have our 3, our 5, and then our sorted collection of 6 and 9. We have another comparison. Is element 2 bigger than is element 1 bigger than element 2? No, it's not. So we're actually done this set. So 5 is now part of that sorted collection because there's nothing else to compare. So we're now at -2, 3, 5, 6, and 9. We only have 2 elements left to check. So one last time, we're going to write everything up top here. So we're at -2, 3, 5, 6, and 9. And we compare. Oh, where's our sorted elements? Our sorted elements are right there. Is element 0 greater than element 1? No, it's not. So that means 3 is now part of the sorted collection. So now, believe it or not, it does actually go that last step, and it's going to say we're currently sitting at this set, but these ones are all sorted, and by definition, -2 is sorted as well, so that leads down into our final step, which is a final collection of -2, 3, 5, 6, and 9, where the whole thing is sorted now. Now look at the difference in work and effort that had to occur to make this happen. Now the thing is, they both only require the same amount of memory to use. They both only require a single temp variable in order to handle the swaps. So they both have one temp variable. Oops. Oh my goodness. There we go. So that means the memory is big O of 1. So it's constant memory. We only need a single integer, no matter what the size of n is. However, for time complexity, well, what are we doing here? Basically, for every single element, we potentially have to compare it against every other element. So this 9 got compared against everything. And then this 3 got compared against everything. And then this 6 got compared against everything. And you know that I can see that the numbers that it's comparing against every step are decreasing. But in the grand scheme of things, that's irrelevant. At the end of the day, we still end up with n times n, which means this is also a big O of n squared algorithm. So these are the first two sorts that we're going to talk about. In the next lesson, we're going to talk about something a little bit more complex, which is a recursive algorithm called the merge sort. And that one's going to have a much different discussion when we talk about time complexity. And the space complexity is variable depending on the implementation of the algorithm. So there you have it, your first two sorts. You're officially geared and ready to go. All we talked about was the logic of how to do it. But now you have to go take this idea and be able to code it. And that's going to be your next step. Good luck on that.